Hey guys, Mrs. Hijik here with your electromagnetic spectrum objective 1 video. Make sure you have set up your Wix. Now the Wix is going to look a little bit different from now on. The W is still the what, the objective, or what you're learning. Today we will understand how radiation on the electromagnetic spectrum is organized. The Q is still the essential questions that you will have to answer as you watch the video. Today there are 7. Make sure you write the question as well as the answer. The S has been the summary. We're going to change that a little bit. The S from now on is going to stand for support, and this is where you're going to find your action item. So instead of doing an action item and a summary, we are going to simply do the action item. So your support today, or action item, is to draw an electromagnetic spectrum and label the 6 forms of radiation. Now I want you to pause the video right now if you need a few minutes to set your Wix up, and when you're ready, hit play. All right, your Wix is ready, so let's go. We're going to start with this video that's going to introduce everything that we will be discussing in today's Objective 1 video.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves, which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by.
Now, all of these waves are moving around you as you're sitting watching this video right now. But not all of these waves, all right, hold on. Let me reverse. Okay, so yes, all of these waves are moving around you right now. But when waves strike an object like you, 3 different things can happen. The waves can be reflected by you. The waves can be absorbed by you, or the waves can go right through you. Most of these waves are going right through you. The radio waves and the microwaves and the cell phone waves and all that stuff is going right through you. The only waves that are not going through you are the visible light waves coming from the TV, or in this case, maybe your cell phone screen or your computer screen. That light is actually interacting with your eyes. Some of that light is being reflected off of your body. But all of these other types of waves, they're just going right through us. Kind of scary to think that all these waves are moving right through our bodies right now. But don't worry, it's not harmful. We'll talk about that in a little bit. Oops. Nope, go back. Nope, go back. Oh no, it started all over. All right. There we go.
And waves from your neighbor's Wi-Fi and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
All right, so let's talk about some of the things mentioned in the video. First of all, a wave is defined as a disturbance that transfers energy from place to place and is described by its wavelength. Now this little symbol here is the Greek symbol lambda, and it is a shorthand way of writing out the word wavelength. So you can write lambda in place of wavelength and they mean the same thing. So wave examples do include sound. Sound travels as a wave, so does water, and light. And sound, water, and light is simply transferring energy from one place to another. Now sound and water, they both need a medium to travel through to move their energy, but light radiation does not. Light can travel without a medium through the vacuum of space. So energy can be transferred or moved from one place to another through empty space, the vacuum of empty space, but only light can do that. Here's a picture of a wave that we are going to, oh, there's stuff in the washer. Don't worry, I'll get that. There is stuff, sorry. So here's a picture of a wave that we're going to use to discuss two characteristics you need to be familiar with. Wavelength, which is the distance between the same point on two waves. And you can see here's lambda, lambda, lambda. And it's measuring the wavelength, so from crest to crest, or even from the lower part of the wave from a trough to a trough. But measuring the distance between two waves from the same point of one wave to the same point on the next is called wavelength. And some forms of light have very, very long wavelengths, like we saw the radio waves that can have wavelengths up to a mile or 2 miles in length, or waves, types of radiation that have very, very, very short wavelengths, like gamma rays that have wavelengths that are in the billionths of the meter or the nanometer. Now, the wavelength of the wave will determine the frequency of the wave, which is the number of waves that pass a point in 1 second and is measured in the hertz. The longer, the more spread out the waves are, the lower your frequency is going to be, because not as many waves will pass a point in 1 second. But the closer the waves are together, the shorter the wavelength, then the more waves will pass a point in 1 second, which will have an increase in frequency. So let's say that this is 1 second of time. We count there is 1 and 2 waves within that 1 second time interval. So we would say the frequency of this wave is 2 hertz. Electromagnetic radiation is nothing more than energy emitted or released in the form of a wave or a photon when electrons move from a high energy level to a lower energy level. And we've talked about this process already in our atomic structure Objective 3 video, but let's quickly review. Our electrons are orbiting the nucleus in the electron cloud, and when those electrons absorb energy from their surrounding environment, that electron will jump up to a higher energy level. But this is an unstable state, so that electron will quickly fall back down to its original level, and in the process of falling, it will release a photon of energy, a little packet of energy. And the amount of energy in that packet will determine the form of electromagnetic radiation. Now, if enough energy is absorbed by the electron, when it jumps up, it will actually jump right off of the atom itself, causing the atom to become a positively charged cation. If the electron leaves the atom, then I have more positive charges in my nucleus, so an ion has been formed. In this process, ionizing radiation will be produced by the atom. This is a very high energy radiation, which is harmful to any object that it encounters. But please remember, EM radiation is nothing more than light, which is produced during this process of electrons jumping up, falling back, releasing energy. So it's just light. Now, these forms of light or radiation or electromagnetic radiation can be organized on the spectrum, and they're organized based on their energy and their wavelength. So we start with the longest wavelength wave, which is our radio wave. And as we move across the spectrum, the wavelength is getting shorter, so the waves are getting closer together, which causes an increase in the frequency of the wave until we get over here on this side where our wavelength is the smallest and our frequency is the highest. Now, there are 6 forms of energy that we find on the spectrum. We have radio. Now, microwaves are also forms of radio waves, so these kind of go together, radio and microwaves. They have very similar wavelengths, very long wavelengths. Microwaves are simply shorter wavelength types of radio waves. And then we have infrared, which we have learned already is referring to any heat or thermal energy. Then we move to the visible part of the spectrum, which is the only part of the spectrum that can be seen by the human eye. Our eyes are only sensitive to the frequency, this very small frequency range within the visible light part of the spectrum. Beyond visible light, we move into forms of radiation which become ionizing. Remember, those are the forms of radiation formed when the electron jumps right off the atom and positive cations are formed. When this type of radiation is formed, we're talking about radiation that can be harmful. So ultraviolet radiation or UV, that can be harmful, and so can X-ray, and so can gamma. So we have to take precautions to protect ourselves from these ionizing forms of radiation that have very short wavelengths and very high frequencies. So what does light do when it strikes matter? I kind of talked about this a little bit when I paused that intro video. Anytime light is incoming and it strikes an object, 3 things can happen. The first thing is that some of that light can be reflected. So this green leaf is reflecting green light, and we see the color green, and so that is the light that's being reflected. It's the color that we actually see. Now, all of the rest of the light frequencies are being absorbed by the leaf. And then some forms of radiation are actually moving right through it or are being transmitted. So our longer wavelength waves like radio, microwave, those have a tendency to go right through most objects, including you and me. Other forms of radiation can be absorbed. For example, if we're out in the sun, our body is going to absorb ultraviolet radiation. Or if we're getting an X-ray taken at the doctor's office, our body will absorb that X-ray radiation. If we are close to a nuclear reactor that's having a meltdown, then our bodies will absorb that gamma radiation. So the shorter wavelength forms of radiation will be absorbed by objects generally, not always, but generally. The longer wavelengths will just be transmitted straight through the objects and they're not harmful at all. But then some will be reflected. So when we're talking about color, the color of the object that we see depends upon the wavelengths of light that's being reflected back to our eyes. So if short wavelength waves are being reflected back to our eyes, we're going to interpret that as purple. Or if long wavelength waves are reflected back to our eyes, then we're going to interpret that as red. So we will see whatever color or whatever wavelength, whatever frequency of light that is being reflected by the object and that strikes our eyes, we will then see that color. All the other colors, all the other frequencies of colors are being absorbed by that object. We can also use the spectrum to study parts of the universe, and we can, for example, this Whirlpool galaxy being seen through a telescope with a radio wave filter versus an infrared wave filter versus an optical filter, which just lets us see the colors in the visible spectrum, and then the ultraviolet filter and an X-ray filter. And we can learn what these galaxies are made up of, how much, what their temperature is according to the infrared radiation that's being emitted, and things like that. So it's pretty cool to use the electromagnetic spectrum to study the universe around us. We can also use it to study specific stars. We can look at stars through telescopes that have these specific filters, like an infrared telescope, an ultraviolet telescope, an X-ray telescope, and we can see how much of different forms of radiation are being emitted from those stars. So what is the speed of light again? Remember we talked about the speed of light when we were talking about measuring distances in space. What I want you to understand now, since we're now studying light, is that all forms of electromagnetic radiation travel at the same speed, whether it's a radio wave or an infrared wave, visible, ultraviolet, X-ray, or gamma. It doesn't matter. They're all light. So they will all travel at the exact same speed. Radio waves will travel just as fast as gamma rays, and ultraviolet rays will travel just as fast as visible light rays, and that is 186 miles per second, or 360,000, I don't think I said 186,000 miles per second, or 360,000 kilometers every second. And Einstein's famous equation, E equals mc squared, the C is the constant speed of light. So energy equals mass times the speed of light squared. All right, guys, don't forget to do your support item, and I'm out.